Hi everyone, so this is John, your lab instructor for 118C. This video is just a very short, kind of quick overview of H-NMR for things that should probably be helpful, things that you should know. Hopefully a lot of this is review, some of it may not be. Hopefully it helps clarify the stuff that may not be review, that you may have seen or are not super familiar with, but with how to do or how to interpret, but that you have seen before. Okay, so the first thing is, what is H-NMR? Oops. All right, H-NMR is hydrogen nuclear magnetic resonance spectroscopy. So that's what it stands for, right? You probably already knew that. So things that are important in H-NMR. If you're given a spectrum, is first the position of your signals. Second, it's the number of signals that you have. We'll talk about all of these in a bit. Three is the intensity of signals. And then four is the spin-spin splitting of the signals. So this is things like doublets, triplets, doublet of doublets, triplet of triplets, so on and so forth. So first thing to recall, if we review the position of the signals and why they are in the places they are, first thing you want to remember, right, is that the position of the signals depends on how shielded or de-shielded. Kind of use them interchangeably. If it's more shielded, it will have a certain effect, more de-shielded, right? They are inverses of each other. So it's either it's more shielded, it's less de-shielded, right? And vice versa. But it depends on how shielded or de-shielded the atom is. Right, so for de-shielding, right, this is caused by the presence of an electronegative atom. Right, so de-shielding refers to, give me 1 second. De-shielding refers to the withdrawal of electron density around a certain atom. So if you have hydrogen that is next to a carbon, right, they are relatively the same, right, electronegativity. And so there is no really de-shielding effect due to the carbon-hydrogen bond. However, something like an alcohol, right, an oxygen bonded to a hydrogen, that will have a significantly bigger de-shielding effect, right? Oxygen is very electronegative. Hydrogen is not very. And the oxygen is going to pull that electron density away from that hydrogen. So when it pulls that electron density away from the hydrogen, that causes this de-shielding effect, which causes it to be a higher ppm shift. So the ppm shift has to do with magnetic field and stuff. I believe I sent some notes out, or the notes I sent out, if you're watching this. should be all on there. So the more deshielded it is, the higher the ppm will be. All right. So again, this all has to do with the decrease in electron density around an atom, but in this case, we're specifically talking about H-NMR, so around a hydrogen, right? So yeah, that's it. Intuitively, right, deshielding is pretty easy to get the concept of. If you already have a good grasp of electron density, right, and the different effects. So another example, right, would be an aldehyde group. So an aldehyde group, if I were to draw that out, something like that, the hydrogen is not directly connected to an oxygen, right? However, it is connected to this carbon right here, which is part of this carbonyl or has a carbonyl functional group, right? This whole thing together is an aldehyde. So the C double bond O withdraws electrons up that way, right? There's a dipole moment. The oxygen is significantly more electronegative than the carbon, and it's participating in a double bond. So if you can recall, right, this carbon is partially positive, this oxygen is partially negative, and so some of the electron density is getting pulled up kind of through that carbon to the oxygen away from the hydrogen. That's why aldehydes, right, on H-NMR are also at a high ppm shift. They're very downfield on the spectrum. So most H-NMR signals occur between 0 and 12. So these are all pretty much all the functional groups that you know are going to be between there. There is a large, oops, or let's just say there are many signals signal types, right? Differing functional groups. Between 0 and 6. So there is very little variance really above 6, right? Generally, if there's some sort of shift that's above 6, it's easy to pinpoint which one it is, right? So you have your chart. I have a different chart here. But on your chart, right, you can look, there's not too many things that are going to be greatly above 6, and where they are, right, you're not going to have like a whole bunch of things at a ppm of 8 or 9 or 10. It's like one thing at around 12, one thing at around like 11 and a half or 10 and a half, right? So there's also kind of a large gap between each of these functional groups. So talk about the number of signals. So I won't get into the phenomena of alkenes and alkynes, right? So, and benzene rings. To put it very shortly, right, you don't have to know this, but for anyone who's interested. So benzene, in the way that the electrons are aligned with the pi bonds, the magnetic field that is used, right, in NMR creates a ring current in the pi electrons, which amplifies this magnetic field that is being applied, which is why it causes a downfield shift more than you would maybe think, right, that it would. More causes a bigger deshielding effect of the hydrogens, and the same as with the alkene, right? The alkyne is actually upfield or a lower ppm from the alkene and the benzene, because if you actually draw it out, the alkyne, once the magnetic field is applied, the ring current that forms, or I guess is made from this, opposes the magnetic field. And so since it opposes this magnetic field, it actually causes the ppm shift down, or up field, but down in number. All right, so the next thing we want to talk about is the number of signals. So if two protons, right, in this case it's H-NMR, so this can also be applied to C-NMR, so you could say atoms, but if two atoms, in this case protons, the hydrogens are identical, they will have the same shift. That means one signal, right? So if they are chemically equivalent, right, I'm only going to get one signal on my spectrum. They are indistinguishable from one another. So just as a quick practice, right? And so this means that the inverse is also true, right? If I have two protons that are not identical, then they will not have the same shift. So let's do a little bit of practice. Let's see how many H-NMR signals for each molecule. So let's start off with this molecule right here. Right, so if I go ahead and I draw the hydrogens in, I'll do this with blue. And I will label with orange. All right, so first I can see that these two hydrogens are on the same carbon, and they are going to be equivalent. So these I'm going to denote with an A. These two hydrogens are also equivalent to one another. Right now, I'm not going to denote this with a B though, right? So if I actually, let's just do it right now. They are going to be the same, but let's see. So if these are two different signals, HA and HB, right, then both of these hydrogens, or all of these two sets of hydrogens, I should say, should be chemically unequivalent. Let's check. Up here, these two hydrogens are connected to a carbon that is next to a chlorine, and then next to a carbon with a chlorine, right? These two hydrogens are connected to a carbon that's connected to a chlorine that's next to a carbon that's connected to a chlorine. So these actually are going to be equivalent. You can kind of just, as I did there, right, follow it down, see if it's the same. And you can see that there is an equivalence, right? There is actually a symmetry here, is the way you can view it. Across this molecule, and then those hydrogens are equivalent to one another. Typically, when there is symmetry, you will have some sort of equivalence. So generally speaking, that's true. All right, the next one is, what if I change this up? What if instead I had a chlorine here and a bromine, and then I went ahead and just labeled the hydrogens in blue again? All right, so I'm going to denote these two hydrogens with HA. They are equivalent. But what about the ones on the bottom here? So these hydrogens are connected to a carbon that's next to a chlorine, but these hydrogens are connected to a carbon that is connected to a bromine, right? It's different from the case over here, where the halogen was the same. So these are actually different. They have a different chemical environment, and so those are going to give off a different signal. All right, another one. it would be like this. So I will not draw all the hydrogens in just for the sake of time. Right, but all the hydrogens on this carbon, let's denote this with an A, are going to be the same. Same thing with all the hydrogens on this carbon. They are going to be denoted with a B. Why? Because the hydrogens on this carbon, hydrogens A, I guess we could call this carbon A, but the hydrogens over on this carbon are farther from the alcohol than the hydrogens on this carbon, right? They're not the same. Then this hydrogen is also not the same, right? Because it's connected to the oxygen directly. So we have three different types of hydrogens here, different sets of hydrogens, and they will give off 3 signals in total on the spectrum. All right, if I were to do something like this acetic acid, same thing, right? The hydrogens over here will give off a unique signal. There are no hydrogens on this middle carbon. There is, however, one over here. So we're going to get 2 signals for acetic acid. And I should actually start writing these down. So this was 1, 2, 3, and 2. All right, what about something like this alkene? What about this? And I'm actually going to redraw this. All right, so let's start with the easy one. The one on this carbon is unique, right? It's connected to the carbon that is connected to the chlorine. All right, but what about these two? So you may be tempted to put B for both of these, right? All right, they're chemically the same. They actually are not. So something to keep in mind, right, is across a double bond, you cannot rotate it, right? A single bond you can rotate around. You can kind of orient it however you want. However, right, in a double bond, you cannot spin it around. So these are fixed in space. What does that mean? That means that this hydrogen is permanently fixed closer to the chlorine, and this hydrogen is permanently fixed farther from the chlorine. Right, so this hydrogen is always cis, and this one is always trans to the chlorine. Should have done that in blue. But these are not going to be equivalent. And so this hydrogen will be HB, or you could do the other way around, B on top, C on the bottom, or any order you want, but they are not going to be chemically equivalent. So I've denoted HB on the bottom hydrogen and C on the top for no particular reason for the order of that. So this is going to be 3 signals here. Right, when they are fixed in space, make sure you consider this. So things across an alkene, right, consider that they may not be equivalent. Things that are fixed in a ring, right, if you have a ring of sorts, actually we'll see one in a second, so I won't spoil it, but if you see things in a ring, right, if you have something that is on one side of the ring, like a halogen or an oxygen that is permanently fixed in space there, right? Hydrogens will either be on the same side of the ring or they'll be on the opposite side. And so do consider those things. All right. Last one is, what if I had this molecule here, right? Again, one may be tempted to say, all right, well, the hydrogen off of this carbon is going to be A, that's 1, and then both of these carbons are equivalent. It's not going to be true. So, I mean, both the carbons are equivalent, but not all the hydrogens on each carbon are equivalent. So if I were to draw this picture a little bit better, Instead, what if I drew it like this? Where chlorine is on a wedge, the other hydrogen is on a dash, and then I have the hydrogens on the other carbons here. All right. Well, this hydrogen is all by itself. It is unique, so that's going to go up a signal. It's closest to the chlorine. Right, now what about the other ones? Right, so again, think about how it's oriented in space. So if you have this chlorine coming towards you, right, on the wedge, you have these two other hydrogens that are on the same side of the ring going towards you. Those hydrogens will be closer, right, to the chlorine than the hydrogens on the dash pointing away. So these hydrogens are not equivalent to each other. Specifically the hydrogens on the wedge versus the dash. So these hydrogens on the wedge are not the same as the ones on the dash. Well, you may be asking, why are they the same denotation, right? Why is it both two HBs and two HCs? Because the carbons are equivalent, right? So they're both connected to a carbon, which is connected to another carbon, the other one, which is the same thing. And those are connected to the other carbon with the chlorine, right? The carbons are equivalent. There is symmetry here, as you can see once again. And so those hydrogens on each carbon are not equivalent, but the hydrogens in the specific oriented in space in a specific way. So on the top carbon and the bottom carbon on a wedge, those are chemically equivalent. And then that's it for this. All right. So this is going to be 3 total signals. Again, make sure to consider how they are oriented in space to get the correct number of signals. So there's a test you can kind of do for testing for this atom equivalency. So let's write it out. So for this test, the first thing you want to do is draw 2 versions of the molecule. Right, molecule in question. Yeah, just make sure to pay attention to your stereocenters. So just first draw 2 versions of the molecule. Make sure to pay attention to stereocenters or stereochemistry. Second thing you want to do is in one version of your molecule, replace one of the atoms right? One of them in question, right? You're questioning whether 2 atoms are equivalent. So pick one that you're questioning whether it's equivalent to the other one or not, and replace it with a Z, with imaginary atom Z. In the other version, replace the other atom with the imaginary atom Z. Now, this can go a few ways. Right now, you're going to compare the two resulting molecules that you have. And we're going to do a few examples after this too. So if the molecules are the same, that means you can superimpose them on each other, right? If the molecules are the same, then the atoms are homotopic. So yeah, they're basically the same. It's kind of a fancy word of saying they are chemically equivalent, and they pretty much are equivalent in every way. All right, next is if the molecules are enantiomers. So this is something you should know by now. Right, where they are mirror images of each other. So you can think about it in terms of stereochemistry. One has an R stereochemistry, one has an S. All the stereocenters have to be flipped. So if a molecule has one stereocenter, right, the molecule of the R version is the enantiomer of a molecule of the S version. If it has two stereocenters, an R molecule is an enantiomer of the SS molecule, right? And keep going, RS versus SR, so on and so forth. So if they are enantiomers, if the two molecules are mirror images of each other, right, that's what enantiomers are spatially. So you can think of your two hands, right? Your hands are mirror images of each other, right? I cannot superimpose them right on top of each other. However, if they face each other, right, they mirror each other well. So if the molecules are enantiomers, then the atoms are enantiotopic. All right. The next thing is if the molecules are diastereomers, then the atoms are diastereotopic. Right, just to recall, diastereomers. So it's a relationship between molecules, but you can't have one molecule and say it's a diastereomer. It has to be related to something else. Kind of like family members, right? You can't say I am brother or cousin, right? The who. So diastereomers, right? That's where some, but not all of the stereocenters have changed between molecules. So this doesn't work for molecules of one with one chiral center. It only works for molecules with more than one. So things like RS and RR, those are diastereomers. RS and SS are diastereomers. SR and RR are diastereomers, right? So on and so forth. So it's where one or more, but not all of the stereocenters have changed. This is the typical definition of it. So if the two molecules are diastereomers, right, when you change out the atoms in question, right, in this case it's hydrogen, to see whether they're homotopic, enantiotopic, or diastereotopic, or completely different, as we'll get to in a second. Right? If the results are diastereomers, then they are diastereotopic. We'll talk about the implications of this for the signals. And then the last thing is if the molecules are structural isomers, they are completely different. So this would be like changing out an H that's connected to an oxygen and changing out an H that is connected to a carbon, right? Those are completely different. If you were to put the Z in their spot, right, they would be structural isomers with the Z in different places, but they're completely different. All right. So covered that. So homotopic atoms, let's cover that first. Homotopic atoms are identical to each other. That means they only give off one signal. All right, now let's go on to enantiomers. So if you recall, enantiomers have identical physical properties aside from the rotation of polarized light. Let me write that in. So therefore, enantiotopic hydrogens or atoms will have the same chemical shift. Once again, that just means there is one signal. Now, the last one is diastereomers. Right, if they're completely different, of course, they'll have two different signals, so we're not going to write that one down. But diastereomers do have different physical properties. So therefore, diastereotopic hydrogens or atoms will have different chemical shifts. So the two atoms in question will give off two different signals. So let's do a little bit of practice. We're going to use the test. To determine how many H-NMR signals could occur. Also, I'm going to denote some of these hydrogens with HA and HB. So we're also going to give the relationship between the two atoms that are in question. So let's start off. Let me underline this. Start off with this. All right. So HA and HB are the two atoms in question. Now I will draw in the rest of the hydrogens over here on that methyl group. So let's do the test, right? If I want to test if these two hydrogens are equivalent, we're just going to follow what we said before. So first, I'm going to draw two copies of the molecule. One where I replace one of the molecules in question. Right, so the A and B don't denote that they're actually different. It's just to see these are the ones we're testing whether or not they're equivalent, but they're still both hydrogens. So I'm only going to put an H, not an HB, right? Otherwise, then they will be different. All right, so HA and HB are just the hydrogens in question. So one where I replace HA with Z, then I will take another molecule where I replace HB with Z. All right, now if I was to do the stereochemistry of this, right, figure out what it was, let's just say Z is the highest priority. It doesn't matter as long as you keep it consistent between both of them, right? If I was to make a Z the highest priority in this one, it would be Z, then bromine, then the methyl, and then the hydrogen. So it's going to be, yep, it's going to be S, right, versus the one over here, Z, bromine, methyl, and a hydrogen. Looks like it's S, but the lowest priority is not on a dash, right? So the easy way to fix this is just reverse it. So instead of S, it's actually R. If you switch any two groups, you'll change the stereocenter. So if you haven't learned that, that's a quick way to do it, right? You don't have to reorient the molecule in your head or on paper. Just do it as you normally would. And if the lowest priority is not on a dash, then just take the other stereocenter, right? All right, so you can see that these are opposites, right? They're actually enantiomers of each other. Also to note, right, there is no other stereocenter or chiral center in this molecule, right? We just have the bromine, which is not, and then we also have the methyl carbon, which is also not, right? It has 3 hydrogens. So these stereocenters are different from each other. And we would say that these are enantiomers. And because these are enantiomers, these 2 hydrogens are enantiotopic. All right, not too bad, right? All right, let's go. And so the total number of signals here ends up being 2 signals, right? Because I have all the hydrogens. I'm just going to do this in red. The hydrogens up here. Just denote that with an A. And then I have the hydrogens down here with a B, right? Because they're the same. All right, let's go on to the next. So next example is if I had something like this. All right. So first thing to note, right, the hydrogens in question are the ones on the bottom. So let's label a few of these hydrogens first. So the ones on top, right, these are in fact 2 CH3 groups. I will not draw them all in for the sake of, space. But these CH3 groups are equivalent. So all these hydrogens are also equivalent, right? They can freely rotate around. They're not stuck in space. So sometimes they'll be closer to these hydrogens where one will be, but they'll spin around. So those are equivalent. Now these hydrogens over here, right, are connected to this carbon, which is stuck in a ring. So we have to consider, right, the spatial things about it, right? Whether or not the hydrogens are on the same side as something on the ring or opposite, right? whether or not they're chemically equivalent. So the hydrogen on a wedge is on the same side as both the methyl groups, versus the hydrogen on the dash is on the opposite side from both, again, both the methyl groups. So that means that this hydrogen has to be different from this other hydrogen, because one is always closer to both the methyl groups, right? It's not this ambiguous one of the methyl groups, right? And the other one's closer to the other. It's on the same side as both, and the other one is just always on the other side. All right, now we do have to question whether or not these other two hydrogens are different or are the same, homotopic, enantiotopic, or diastereotopic. So let's just do what we did before. Let's draw the molecule twice. We're going to go ahead and replace this with a Z, the first one, HA. And then we're going to compare it to the other one. Okay, great. All right, well, if you're looking at this, something that should be, I mean, you could do the stereocenter stuff. I'm not going to, because if you look at this, something that should be pretty clear is that these are mirror images of each other. And because of that, these are also enantiomers, which means, right, that the resulting hydrogens, or the, sorry, the hydrogens in question, not resulting hydrogens, the hydrogens in question, HA and HB, are enantiotopic. So they will give off the same signal, and let's just denote those both with a C. Oh, wait, there's already a C. I lied. Let's do a D. So there is going to be 4 signals in total. All right, last one is going to be this. So I have this molecule where HA and again HB are the atoms in question. So if I go ahead, I mean, so first we can label some hydrogens, right? This one, these ones on the end are clearly different from this hydrogen, which are clearly different from those, right? Hydrogens on that methyl group are next to a carbon with a chlorine. That hydrogen next to the chlorine is by itself, connected to the carbon with the chlorine. Then the other one, group C, right, is a methyl group that is not connected to a carbon with a chlorine. So those are all different. But now let's go ahead and do our test one more time. I'm just going to draw it twice first and then put in the Z's. Oops, I forgot my chlorine. So in this one on the left, I'll replace HA with Z, and the one on the right, I will replace HB with a Z. All right, well, these are not clearly mirror images of each other, so why don't we check the stereocenter? So if I were to do the stereocenter of this carbon, again, let's just pretend Z is the highest priority. As long as you keep it consistent, it doesn't matter. But let's say Z is the highest priority. So 1, Z gets the highest priority. then the carbon with the chlorine, right? Because the other carbon has hydrogen groups. Then it's the carbon with the hydrogen groups, and then it's the hydrogen always at the lowest priority. So you can see this is an R, right? Stereocenter. To double check, right? The hydrogen is the lowest priority and it is on a dash. Do the same thing here. Z is first priority. That is a second priority. This is the third priority. This is 4. It looks like R, but hydrogen is not on a dash, right? So instead it's S. Just flip it. So this is R and this is S. Oh, great. So they are an antiotopic hydrogens, right? No, they are not, right? Because we also have this other stereocenter to worry about. So this stereocenter, fill the note with a star, is different. However, this carbon stereocenter is going to be the same. I will not go through it. Reason is you could do it yourself if you would like, right? But we're not switching any groups here. So the hydrogen is still a hydrogen, the chlorine is still a chlorine, the methyl is still a methyl. And so then the carbon group with the Z is the highest, or the second highest priority, right? The chlorine is the second highest. So it's the same. But those are the same stereocenter. Oops. So what does that mean, right? If you're looking at these two molecules, these are diastereomers, which means that these two hydrogens are diastereotopic, which means they give off two different signals. So that means this one we'll say is signal D, and that one is E. So we have 5 signals in total for this molecule. All right, so that is how you can check for equivalency, right? This is talking about homotopic and antiotopic, diastereotopic hydrogens, or I guess they're completely different, but we didn't show an example here because generally they're on different carbons completely next to different things that are going to be completely different. So you still can, however, right, use this to check, right? Let's say if you're unsure if they are equivalent or not, right? You still can, right, do the same test. So to do that, even if the hydrogens are in different carbons. Kind of like an example too, right? They may be further apart. All right, the next thing that we want to go over is going to be the strength of signals. So this is the third thing. So if you recall Beer's law, right? Beer's law states that the quantity of electromagnetic radiation absorbed is proportional to the number of moles of the substance that is absorbing the radiation, right? Maybe it's never been said like that, but that's what it is. And so, right, usually it's a light experiment where you have a spectrophotometer. I believe that's the correct word. Could definitely be wrong. But some UV vis machine, right? You shoot light through, it absorbs a certain amount of light at a certain wavelength. And so what you are measuring, right, is the amount of electromagnetic radiation, the light, right, being absorbed. And the higher the concentration, right, the more moles of substance you have in the solution. And so it's linearly, it's proportional. It's a linear relationship, as you have probably seen in Beer's law experiments, where you draw the graph and stuff. So in other words, the area under a signal will be directly proportional to the number of hydrogen atoms giving rise to that signal. Right. And again, you can think of this in terms of Beer's law. So I will write that down really quick, just in case anybody wants it for notes or the video. So common terminology, the area under the curve. Oops. Is called the integral or integration. Usually referred to as the integration. Right? This just comes from calculus. So for those of you who have taken calculus, I think most of people have if you're taking this class. Calc 2, right? You take integrals. So integrals is the area under the curve of a graph. Right. So if I were to give some sort of graph, right? Like let's say I had something like this. I won't label all the ppm just for the sake of time. Actually, give me 1 second. Here we go. Where all the bottom axes here are ppm. Right, so if I start with this first graph, I'm going to draw a peak here without all the splitting stuff, and a peak right here. So if the graph tells me I have an area of one area unit, I'm going to actually denote AU. Usually that equals for arbitrary unit. So let me do a small a. AU will be equal to area unit in all of these. So that's one area unit. And then over here is 3 area units. And let's say the molecule is this, right? So if I were to label these peaks or assign these peaks, right? This carbon on the left has 3 hydrogens. We'll call that A. And then this hydrogen on the right, if there's 1, I'll just call this hydrogen B. So the peak on the right has an integration of 3, right? Remember, it's directly proportional to how many hydrogens there are. So the bigger one is going to be correlated to the one with more hydrogens, since there's only 2 here, right? And then the smaller one is correlated to the 1 hydrogen, right? And so you can see the numbers match up too. 3 AU area units for the carbon with 3 or the 3 hydrogens, and then 1 area unit for the 1 hydrogen. All right, another example is what if I had something like this. All right, if I were to label these hydrogens, right, these sets of hydrogens are equivalent. They're both connected to a carbon, which is connected to an oxygen, which are both connected to the same quaternary carbon. And then the same thing with these hydrogens. So which one is which? All right, well, as we talked about, right, with shielding and deshielding, the closer it is to a an electronegative atom, the more d-shielded the hydrogen will be, which means it'll be more downfield or at a higher ppm. So this peak, oh, and I forgot to label the area units. So this is 6 area units. This is also 6 area units. So this peak on the left is going to be correlated to hydrogen's A because it's closer to an electronegative atom, higher ppm shift. And then this peak on the right is correlated to hydrogen's B. All right, for the next one here, let's say I had something like this, where this said I had one second, where this said I had 1.5 hydrogen integration or area units. I should say that's more accurate. And this peak on the left had 1 area unit. And let's say that the molecule in question is this. Once again, I'm going to label these hydrogens. So these hydrogens on these methyl groups at the end, right, connected to the oxygens, they are equivalent, these sets of hydrogens. And these hydrogens in the middle are also equivalent. So if you're looking at this, right, well, how do you interpret this? It says 1 is 1 area unit, 1 is 1.5 area units, right? So what do? You need to multiply these to be some sort of number that makes sense for your molecule. Typically, if you're given a molecular formula, right, then you can just multiply the total integration, right? So let's do that here. Total integration is going to be 2.5. Multiply it by a number to get the total number of hydrogens. So let's count how many hydrogens we have here. So I have 3 from this methyl group on the left. I have 4 from the ones in the middle, so that's 7. Then I have 3 more, which is 10. So to get the 10 hydrogens, I need to multiply the total integration by 4. Which means I multiply each of these individual peaks by 4. So this one is actually going to be 4 area units. I just scale the whole thing up. And this one is 6 area units. So now we can just label them, right? The one with 6 is going to be hydrogen's A, because there are 6 of them, and then B because of that, right? And so keep in mind, right, why is B bigger than A? You have to take a look at your chart. So CH2s are generally more downfield than CH3s, right? And they're both the same proximity to an electronegative atom, but that's why there's that difference between them. All right, last one. The molecule in question will be ethyl bromide. Like that. And let's say I had a peak over here. Again, we're not looking at any complex splitting or stuff like that. And then one over here. This one's not so bad. So I have 2 peaks. This one has an area of 1 AU, and this one is 1.5 AU. Oops, no, messed that up. No, that wasn't messed up. My bad. 1.5 AU. All right, I have 5 hydrogens in total in this molecule, so I'm going to have to multiply the total integration by 2, right? 1 plus 1.5 is 2.5 times 2 gives me 5. So this is 2 hydrogens that I'm expecting from this peak, and I'm expecting 3 hydrogens from this one, right? This one's pretty easy to tell. That with A and this one with B. this is going to be A, and this is going to be B. Also makes sense, right? The one next to the electronegative atom, bromine, is further downfield, higher ppm. All right. Now, if I were to actually draw this last one more accurately, it wouldn't look like this. And these ones, I guess, I draw it up, but these would all be singlets as well, something that you all are probably familiar with. Right, this last one would actually look something like that. And something, I mean, a lot skinnier, but something like that. And something like that. Right, this is probably the shapes that you're more familiar with or have seen. So this, once again, has an integration of 1 area unit, and this was 1.5 area units. So if it's your first time seeing NMR, which I think for most people, or if not all the people watching this video, it's not, right? But for the people who are first seeing NMR, this may come as a surprise. Right? If you have seen CNMR first, then you would expect only 2 peaks, right? You have 2 sets of equivalent hydrogens. However, in this case, you get this splitting pattern is what we see. Right? And the other ones, they don't have a splitting pattern. They're actually, it's by design, right? They're all going to be singlets. We'll talk about that in a second. For those of you who have had experience with NMR, right, they are all singlets, and you can even double check that. Right? But this last one is not a singlet splitting pattern for either of these. So we see 7 peaks, right? Why do we see 7 peaks? Because we have, something called spin-spin coupling. Which is going to be the 4th thing that we talk about. So let's consider this substance. So when, again, for those of you who have, who I sent the papers out to, right, this should look, the next part should be familiar. For those of you who have not, you might want to take a read. And for those of you who don't have either, then I want to watch a video on the background of nuclear magnetic resonance first. So in a sample of this molecule, when HA, hydrogen A, is in resonance with the radio frequency that is being used, we're going to draw a diagram showing the spins of HA and HB respectively. This is to explain the phenomenon of the splitting patterns. So you can skip this part of the video if you don't care, but this is where it comes from. So if you apply this magnetic field, V naught, these are going to show the different hydrogens, right? I have two HAs and I have one HB. So the first way that they may be lined is like this, where HB is in line or going with the magnetic field, aligned in the direction of the magnetic field. Or we have the other case where HB is aligned opposite to the magnetic field. And so you recall, right, the position of the signal. Right? This was the first rule. Depends on the magnetic environment of the atom. Or let's be more specific, let's say of each proton. And that is affected by electronegative atoms. So how many peaks or will we see for HA? The amount of peaks we'll see. We're going to draw them. And we're going to see two peaks, right? Why two peaks? Because we have two different magnetic environments. Right? We have one where the spin of HB is up and one where the spin of HB is down. So we see two peaks as a result of this. That looks something like that. And again, that is a result, right, of the magnetic environment, whether HB is up or down spin. How many signals do we see? We only see one. So what do we call the signal? We call this a doublet, abbreviated with a small d. Right now, I'm going to ask almost the same question. Which in a sample of this molecule, when HB is in resonance with the radio frequency, to draw a diagram showing the spins of HA and HB respectively. So we're going to have quite a few here. Let's see. I have my magnetic field pointed up. I have my three atoms like that. HB is going to be pointed to the right. It's aligned with the radio frequency. Again, double check the CNMR notes if you're confused on where I'm getting this from, the arrows at least. So the first way that they can be aligned is like this, up and up, or I could have them go up and down, or I could have them go down, then up, or I could have them go down and down. Right? If you look at these two are magnetically equivalent. Why? Because HA and HA are equivalent, right? So it doesn't matter which one is up and which one is down. So they're both magnetically equivalent. If one is up and one is down, right, it doesn't matter if the other is the opposite orientation. So how many peaks will we see? Similar question, or exact same question, actually. So how many peaks will we see for HB? Right, we're going to see 3 peaks, and it's going to look like this. And we have the symmetry across the middle. So I didn't say that before, right? But before there was this symmetry. Same thing here, right? How many signals? We're only going to see one signal. What do we call this signal? We call this a triplet, right? Abbreviated with a small t. All right, so this is where the coupling phenomena, or coupling, the patterns that you see, right, come up. So doublet, triplets, all that fun stuff. This is where it comes from. So it depends on the magnetic environment and the different ways it can be aligned, right? Something to note too, right, is why is this middle one tallest? Which orientation, right? Or that's actually what I'm getting at is why is this middle one the tallest, right? So each of these peaks represent an orientation, right? In terms of the magnetic orientation, right, of each of these. So this one could be like that. 2 down spins could be that one. But now there are 2 of these that are magnetically equivalent, which is the middle one. That's why it's the tallest, right? Because they are equivalent to one another, you get it twice as much, and that's why it's twice the height as the other ones. Pretty cool, right? All right, we're going to go on to the next page here. So here I have written down a golden rule. So the golden rule for splitting is if a proton atom has n neighbors, where n is some natural number. For those of you, just need a quick reminder, natural numbers, right? It's counting numbers, so 1, 2, 3, 4, all positive integers, basically. But if you have n neighbors, right, where n is a natural number, then there will be n plus 1 peaks. So actually, that's not correct. I should say integer, positive integers, and also including 0, because you can also have 0 neighbors. So n can be 0 or natural numbers. Some abbreviations, right? A singlet, S, means it has no neighbors. And so it gets 1 peak. A doublet has 1 neighbor, and it gets 2 peaks, right? So you can kind of go backwards from this. 2 peaks, so 2 minus 1 equals n. Right? You could say the number of peaks is equal to n plus 1, right? And then you can just do some algebra here. Number of peaks minus 1 is equal to n. Not too bad. I'll keep that in blue, actually. Not really true for complex splitting, but for simple splitting, it is. A triplet is 3 peaks, quartet is 4 peaks, pentet, sextet, septet, and a multiplet. So just keep going up in numbers, right, one at a time. On the right, I have the area ratios, as we talked about, or as I mentioned at the bottom of the last page, right? How the area of that middle peak was twice the area of the peaks next to it. And again, that's due to the magnetic spin of each of those atoms, right? Where the equivalent magnetic spin comes up twice as much as the other ones. And you can see for all these are all symmetric, right? 1 to 1, 1 to 1, 1 3 3 1, 1 4 6 4 1, 1 5 10 10 5 1, right, and so on. So, what makes a neighbor? What is a neighbor? So when a proton has a neighbor, what are we talking about? So, oops. Only proton atoms, when we're in the context of H-NMR, only proton atoms can be neighbors. And generally speaking. 2 is an equivalent proton. Is never a neighbor. So you can never have 2 equivalent protons, chemically equivalent protons, be neighbors. All right. 3 is neighbors can only be connected to carbons. And 4 is a proton is only a neighbor if it is on the same carbon. They're diastereotopic, right? Same carbon atom, or one that is adjacent So there is one exception to this. Sometimes all protons on a benzene or phenyl ring are all neighbors. Sometimes. Sometimes they're all neighbors to each other. That's why you've seen me, I mean, you have, hopefully you've been doing the H-NMR from what I've been grading, right? You all have. So if you look at the H-NMR, a lot of times it just looks like a messy multiplet, because sometimes they are all acting as neighbors to one another, which is why it's not very clear and well defined, right? Those benzene rings. And so that's why it's easier to just read it as a multiplet, right? You can read the integration and be like, okay, I got these 4 hydrogen atoms here. I know that these are all correlated to the benzene or the phenyl ring, whatever. All right, 5 is if HA, so some hydrogen, is considered a neighbor to HB, then HB must be a neighbor of HA. Right, so if one hydrogen is a neighbor for the other one that causes some sort of splitting, then the other one must cause some sort of splitting for the other hydrogen. So we're going to go ahead and do some examples. So some examples. Going to start with this one again that we saw before. So if I were to draw all the hydrogens in blue, right, these are all equivalent as we did say before. So on your H-NMR, have an integration of actually maybe 1. So or less, so you have to kind of normalize it. But you get some sort of integration, doesn't really matter. They're all equivalent. You're going to get 1 signal and you're going to get a singlet. I'll do this. So signal A will be a singlet. Oops, I was supposed to do that in blue. I'll do it for the next one. So same thing, same molecule that we saw before. These hydrogens are both equivalent. These are both equivalent to each other, but not the other hydrogens. So for this, we end up getting 2 signals, as we said before. And A is going to be a triplet. And for hydrogens B, it's also going to be a triplet, right? N plus 1. So we have 2 neighbors and add 1. So it's going to be a triplet. The next one is going to be this right here. I draw in all the hydrogens in blue, or the remaining ones. That is a unique hydrogen. These are both chemically equivalent. You may be asking, well, John, what about the carbonyl, right? Isn't one going to be closer to the pi bond or the oxygen, right, than the other? No, right, because carbonyls are flat, right? The carbon is sp2 hybridized. It's trigonal planar. So both of these hydrogens are equidistant from that carbonyl oxygen. Next is all these hydrogens. Hydrogen C will denote. In total, we end up getting 3 signals where A is going to be a singlet. It has no neighbors. It can't have any neighbors. It's on an oxygen. So if a hydrogen's ever on an oxygen or a nitrogen or something that is not carbon, it's a singlet. It's always a singlet, no matter what. So A is a singlet. B is a quartet, right? Why? Because I have these hydrogens that are neighbors with 1, 2, 3 hydrogens. And 3 plus 1 is 4. All right, then what about C? C is going to be actually, let's do it first. So C is neighbor with 2 hydrogens. 2 plus 1 is 3, so C is going to be a triplet splitting pattern. That's what we'd expect. Next one, we're going to look at the same molecule here. So we said before, or actually this is slightly different, but these hydrogens are just clearly different. One's closer to the bromine, one's closer to the chlorine. You cannot twist around that bond. Right, so we would expect 2 signals. Right, and as we said, a neighbor can in fact be on the same carbon or on an adjacent carbon, one right next to it. So this signal A has, or hydrogen A has 1 neighbor. So we would expect the signal to be a doublet. Similar, we would expect B to be a doublet. Last one is, what if I have a molecule like this? If I have something like this, right, I can draw on the hydrogens. These hydrogens are all equivalent. Same with these relative to the ones on the same carbon, and same with those. So I do end up getting 3 signals. But what is the splitting pattern? So for A, we end up getting a triplet, right? There's one set of hydrogens that are neighbors with it, and it's just a triplet. So, yep, that's that. What about C? We're going to come back to B in a second. So C has 2 neighbors. It is also going to be a triplet. Now, what about B? So simple splitting would tell you, all right, well, I have 3 hydrogens on the methyl and 2 hydrogens on the other carbon. I have 5 neighbors, so I must have a sextet. However, this is actually not true. What you actually get is what we call a triplet of doublets. I'm going to use abbreviations here. Or you could say a doublet of triplets. So what happens is, because these hydrogen neighbors are not chemically equivalent, we get something that happens that is called a complex splitting, which we're going to talk about next, and is going to be the last topic of this whole video. When you have hydrogen neighbors that are not chemically equivalent to one another, you have this phenomenon called complex splitting. So simple splitting is when it has one type of neighbor, is really what it is. Has like one set of hydrogen neighbors, right? And then there's basically nothing else. When you have different sets of hydrogen neighbors that are not equivalent, then you get complex splitting. So triplet of doublets, right? And actually, that's wrong. I meant to say triplet of quartets, or quartet of triplets. My bad. So the triplet coming from the 2 hydrogen neighbors, right? And then the quartet part coming from the 3 hydrogen neighbors. So something that you probably have seen, right, is a doublet of doublets where it has 2 unequivalent hydrogen neighbors. The reason why you don't see like singlet of doublets just doesn't really make sense. So triplet of quartets, that means one of the neighbors has one set of hydrogen neighbors is 2 chemically equivalent hydrogens, and the other set is 3 chemically equivalent hydrogens. How would this look? It gets very complicated very fast. So we're gonna do a little bit of simple complex splitting. I said simple splitting before, but some of the basics of complex splitting. So the first thing is, what is J? So we talk a little bit about that. So the J value that you may see in spectroscopy is the amount by which the signal is split. So some common J values. J to B. So the first example is something like this. Right, and I should actually put a little example up here. So the amount by which the signal is split. So, right, it's the distance between the peaks. It has units of hertz. So if we consider these examples, HB, like that. So for those 2 hydrogens, this has a coupling constant. Oh, J. Oops, I already said it, so I'm not actually writing it down anywhere, but J is the coupling constant for this pair. It's not something that you really need to know for this class. In the future, probably not either, unless you want to get into spectroscopy. However, this does lead up into the understanding of complex splitting, which is why I'm covering it. So 0 to 3 hertz is the difference for this, or the coupling constant for these 2 hydrogens. For these other 2 hydrogens, like so, the coupling constant where they are cis across this double bond is 5 to 10 hertz. Right, so again, you would see a difference, and I'll cover that. I'll draw some pictures. And then for these 2 hydrogens, it's 11 to 18 hertz, right? So for all of these are all doublets. So for this first one, you'd expect it to be a pretty small doublet like that, where the difference between these 2 peaks is 0 to 3 hertz. Similarly, right, this is also a doublet, but now the distance of the peaks you should end up seeing be 5 to 10 hertz. And then this last one, right, you're going to see an even bigger difference. I'm kind of exaggerating how big it looks, but to get the point across, right, that it's the distance between these peaks that is your coupling constant, or the J value. So these have different coupling constants in different environments. So in actual spectroscopy, you're able to look at the coupling constants, right, between, or with some sort of splitting pattern, and you can say, oh, great, so this hydrogen must have this sort of relationship with this other hydrogen due to this coupling constant. You look at a big table, you look through it, you're like, all right, well, this type of environment makes sense, right? It has this coupling constant, right? So it must mean that it has this sort of relationship where it sits across a double bond. Maybe it's in some sort of ring orientation. There's a whole lot of stuff that I can get into, but I won't. So let's look at this. Let's do an example. What would the signal for HA look like for this molecule? And I actually do want to add one extra note up here, which is this occurs when sets of hydrogens or sets of neighbors are not equivalent. Sometimes you can kind of get away with it, like if you have a big alkyl chain, they're basically some equivalent. So sometimes you may not see the complex splitting because they're so far from other things, even if they're technically not equivalent. They may just look equivalent. So, but you'll really see complex splitting when the sets of neighbors of hydrogens are not equivalent to one another. So if I was to look at this molecule, the complex version, actually, let's do the simple version. So if this would be, and this is not true because clearly HB is not equal to HC. This is not the case. I'm just showing an example. So if that was the case, first we start like this. We have HA, then HA gets split like that. By HB or HC. They are equivalent. And then this is going to be a difference of J, like that. And then that signal gets split again, like that, where these also have differences of J, right? This is if HB is equal to HC. This is not the case. So I'm just showing that this is why triplets occur, right? And why it looks like this. So this is the simple splitting where they are equal to one another, right? And now you can see I have this kind of nicely spaced triple thing. A little far space, but like that, where the area ratios are 1 to 2 to 1, right? And this is what we would call our triplet. All right, now this is not the case, as I just said. I'm just showing this is how simple splitting, this is how you would draw a splitting tree. So you start with your molecule, it gets split by a certain coupling constant, or your atom gets split by a certain coupling constant, and then it gets split again by a certain coupling constant. So the way this actually happens is with complex splitting. So again, let's start with HA up here. Then HA, let's say, gets split by HC, the bigger coupling constant. Right, HC is trans to HA, which has the biggest one. That's 11 to 18 hertz of a difference. Again, so this is how we draw the trees. Then both of these signals get split. Like so, and I'm going to do this in red. both of these now get split, right, by HB. Which we said is 0 to 3 hertz, right? It's on the same carbon. So what does this result in? Well, if I were to draw this now, something like this. So this is our doublet of doublets. Right, or you could abbreviate it with D. I can also go back here and abbreviate this right now as triplet of quartets or a quartet of triplets. Generally speaking, if you were to look at an NMR, the bigger coupling constant will separate them. So you're not going to see, actually, I'm not sure it would be equivalent. Probably draw it out, probably would be equivalent. I don't think the order matters in which you split it. It's just significantly neater if you do the biggest coupling constant first and then the smaller ones. If you do the small ones and then you do the big one, it's not going to be neat anymore. It's going to like cross over each other and stuff, but you still should get the same answer. So this case, it is a doublet of doublets, right? Where I have two chemically unequivalent hydrogens or sets of neighbors, right? Both sets having one hydrogen in it, right? So it says doublet splitting, 2 minus 1. So two sets of unequivalent neighbors both have one hydrogen in it. And I get this complex splitting, a doublet of doublets. So why did this happen? I will write it down. Right, from HA's point of view, or perspective, the neighbors are not equivalent. So a general rule is complex splitting patterns occur or sometimes arise when neighbors are not equivalent. Well, why is it sometimes? It really depends on the coupling constants. So if the coupling constants are exactly the same, you're not going to see anything. If they are almost the same, probably not going to recognize it either. It may be complex, but that's when you may see on an NMR where the difference is big enough where you may just kind of see these peaks get broadened slightly, where instead of having a sharp peak, it'll kind of get fat, right? Because it's splitting by a slightly bigger amount, making the peaks not as sharp. Or sometimes it'll split just enough where you kind of get these doubles of peaks. So it really depends on the coupling constants, whether or not you're going to see this complex splitting. All right. And that's it. I guess one last thing is we can say one last note. When this happens, we treat sets of neighbors separately to make a name. for the pattern. Given by the number of neighbors in set A plus 1 times the number of neighbors in set B plus 1 times the number of neighbors in set C plus 1, right? And so on and so forth. Right, so doublet of doublets, as you saw up here, or triplet of quartets, so on and so forth. All right. That is all I have. I could do one more quick example on the bottom, where let's say that is HA. And then I have this molecule like that. There is one HA that I did not draw in, like that. So if I'm just looking at the splitting of A, it's going to be this, right? So that's A, label these B. Those are both C. So looking at these separately, right, because these are chemically not equivalent, if B was the only neighbor, right, because we're considering them separately, it would be a quartet. If we look at the set C of hydrogens, it would be a triplet. And so I actually think I did the same example back here. Oh, I did. So this is the same example. What a coincidence. So if the splitting is simple, this is a sextet, or more likely what is going to happen if it's complex, it's going to be a quartet of triplets or a triplet of quartets. And that is it. All right, well, I hope this video helped. I hope that helped clear up some things with H-NMR, how to read it, how you can use integration, where the spin-spin coupling comes from and the splitting patterns, as well as some of this complex splitting stuff. All right, hope that helps. I will see you in lab next week. Have a good one.